Hello, welcome to another video in our Calculus 1 series. In today's video, we're going to be speaking about absolute values. We're going to discuss what actually absolute values represent, what is their meaning, or kind of give them a definition. And then we're going to go over some absolute value equations, how to attack those, and then go over some example problems. Then we'll be discussing absolute value inequality equations, and then proceed with some practice problems. So without further ado, let's begin. So what is an absolute value? So let's say we are told that we have the absolute value of x. These lines right here, they just mean that we're trying to take the absolute value of the number. So let's say we have a variable, let's call it x, and we have the absolute value of x. So then the absolute value of x represents the non-negative distance between x and 0 on a number line. So when we look at our number line, we have 0x and negative x. So if I asked you what is the distance between x and 0, you would say, well, that's just simply x. Now, if I ask you what is the distance between 0 and negative x, you might have said negative x, but the answer is x. Intuitively, we're looking at the non-negative distance between the two numbers. So we're looking at how far we actually travel, and that's x. So note, we have this, expression that we can define an absolute value of. So let's say we have the absolute value of x. That equals, this is known as a piecewise function, where we separate a function into two parts. We could say that x, if x is greater than or equal to 0, and negative x, if x is less than or equal to 0, or sorry, just less than 0. Ultimately, it doesn't matter if we said less than or equal to, or greater than or equal to, or vice versa. We just usually define as 0 as positive, even though it's not. But how does this make sense? Like, let's think about this. I'll do a quick example of this for you. So let's say we want to find the absolute value of 3. So on a number line, let's have 0 here, 3 here, negative 3 here. We know that the absolute value of 3 is equal to 3, just by using this, since x is greater than 0. But in the case that x is less than 0, let's say we're trying to find the absolute value of negative 3. What does that equal? Well, we have from right here, then we need to input the negative of that value. So we go negative of negative 3, which is equal to 3. So it's positive. So it might look trippy at first, why are we breaking this down? But we need to have our values always defined as positive for an absolute value, because the absolute value can never be negative. On the number line, that looks like this. This is the value of 3. And going back here, this is the value of 3, representing the non-negative distance between some values. You might also see the absolute value kind of defined like this. The root of a squared is equal to just a. That's because for this guy right here, the domain of the square root only contains values that is positive, and a squared would always yield a positive value. So let's say I said a is equal to negative 4, then negative 4 squared has to equal to the absolute value of negative 4. We know that in here, this is 16, and from what we just discussed, would have to go negative 4. This is 4, and the negative 1 times negative 4 is just 4. So that's why the absolute value can be kind of defined like this. So let's erase this and talk about some properties of absolute values. So properties of absolute values. So the first property we've kind of already looked at, and it states that a number and its negative have the exact same absolute value, which makes sense. A negative number and its positive corresponding number have the same magnitude. So the second one, which we haven't seen before, but comes directly from the first one, states that if we have the absolute value of a product or quotient of two numbers, it is the same as the product or quotient of their absolute values. So this corresponds to the fact, like, let's say we had 3 and 4 in absolute values. If we multiplied those together, that's the same as 3, 4, which makes sense. That's good. And you can test this out by plugging in the negative cases and to see how they turn out. The last property, we're not going to go too much into it, but it's known as the triangle inequality. You don't necessarily need to know this inequality. It states that the absolute value of a sum or difference between numbers is less than or equal to the sum of their absolute values. This result is called the triangle inequality, mainly because it just comes from the geometric fact that the length of any side of a triangle can't exceed the sum of lengths of the other two sides. So if I draw a triangle right here, let's draw this triangle, let's say C, A, and B. We know that C individually is greater than A and C individually is greater than B, but we know for a fact that C itself can never be greater than A plus B. And if that were the case, it would only be a straight line. It wouldn't be a triangle anymore. So you can kind of work that out yourself, or you can look for a proof of that yourself. But overall, just know that that's out there. Great. So without wasting any more time, let's go into some examples. So example 1. And feel free to pause the video and attempt these examples yourself and then unpause to see how you did. So the first one is absolute value of 2t plus 5, and that needs to equal to 4. So solution, how do we attack this? So if you recall, we said that the absolute value, so a number and its negative have the same absolute value, and that's the same for an expression. So we need to consider two cases, one where the expression inside the absolute value is positive and the other when the expression inside the absolute value is negative. So let's do this. Case 1. And this case is 2t plus 5 is greater than or equal to 0. So one is positive. In this case, we just have 2t plus 5 is equal to 4. And now we just solve for t. Simple as that. So you get 2t is equal to negative 1. T is equal to negative 1/2. Simple. That's case 1 done. Case 2. We're going to have 2t plus 5 is less than 0. In this case, we'll put a negative in front of 2t plus 5 is equal to 4. We'll take the negative to the other side, so 2t plus 5 is equal to negative 4. 2t is equal to negative 9. Minus 5 minus 4 is equal to negative 9. And in this case, t is equal to negative 9 over 2. Great. So the last thing left to do is to check our solutions to make sure that there is no extraneous solutions. So we plug our two values of t back into our original equation. So let's do that. Let's call this check. So in this case, we'd go to negative 1/2 plus 5 needs to equal to 4. So 2 times negative 1, or negative 1/2 is negative 1, plus 5 is equal to 4. 4 is equal to 4, so that's good. And then in this case, 2 negative 9 over 2 plus 5 needs to equal to 4. Forgot to put the absolute value sign, but in this case, it works out. Let's put it on this. We'll get negative 9 plus 5 in the absolute value is equal to 4. And that gives us negative 4 is equal to 4. 4 is equal to 4. So in this case, I just forgot to put the absolute value signs first. But overall, it worked out as is since it was the positive case. But just remember to do that when you're checking your solution. But overall, we can see that t is equal to negative 1/2 and negative 9/2. That's our solution. Just box this. Pretty easy example. Moving on. This example, relatively easy as well. We'll follow the same sort of pattern. Okay, we'll be having 8 minus 3s is equal to 9, and this in absolute values. So again, we'll split it up case by case, one for the positive case and one for the negative case. So solution, case 1, whereby we have 8 minus 3s greater than or equal to 0. And in this case, we have 8 minus 3s is equal to 9. Solving for s, we're going to have negative 3s is equal to negative 1. Or sorry, that should just be 1. 9 minus 8 is 1. S is equal to negative 1 over 3. Perfect. Case 2. So in case 2, we're going to have 8 minus 3s less than 0. And then we'd go 8 minus 3s. This, put in negative, is equal to 9. Let's just distribute the negative through. In this case, negative 8 plus 3s is equal to 9. 3s is equal to 9 plus 8. 9 plus 8 is 17. S is equal to 17 all over 3, which is great. And if we check solutions, you can go ahead and check the solutions, but you'll find for the first case that you get 9 is equal to 9 for s is equal to negative 1 over 3. And for s is equal to 17 over 3, you would get the 9 is equal to 9. So they both check out. So s equals to negative 1 over 3, 17 over 3. I really stress checking over your solutions in the end, because sometimes you will get extraneous equations and you need to, extraneous solutions, and you'll need to exclude them from your solution set. Perfect. Let's do one more example. This example will be a bit more involved, but not as hard as it looks. So let's write it down. So let's say we have the absolute value of x plus 2 minus 8 equals to 1/2 x plus 6. You might be thinking that this looks challenging. Don't worry, it's not too hard. We just have to break it down piece by piece. So recall, we said that the absolute value has two cases. So for the first one, let's do this. Let's split this up, and I'm going to move this to the middle just to give me a bit, not change the size, but move it to the middle to give me a bit more room to work with. So we're going to go like this. So we'll have this side be the positive case. So the positive case for the outer absolute value. So that would be x plus 2 in absolute values minus 8 is equal to 1/2 x plus 6. Okay. The negative case, on the other hand, for the outer absolute value would just mean we'd have negative x plus 2 minus 8. This is equal to 1/2 x plus 6. Let's simplify these a bit just to make it easier for us. So this side becomes x plus 2. And then you'll get is equal to, bringing the 8 to the other side, 1/2 x plus 14. And on this side, we'll distribute the negative onto the other side. So we'll multiply both sides by negative 1 and negative 1, just so that we can flip the sign. So we'll get x plus 2, and then we'll get minus 8 equals to negative 1/2 x plus 6. Moving the 8 to the other side, or sorry, it needs to be minus 6. And moving the 8 to the other side, we'll get negative 1/2 x, and that becomes 2. But note, we still have two more absolute values. So we have 1 in one equation and 1 in the other equation. So again, let's split this up case by case. So in total, we'll have 4 different cases we need to address. So let's look at this. When the absolute value of x plus 2 is positive, we'll just be left with x plus 2 is equal to 1/2 x plus 14. To the other side, when x plus 2 is negative, we'd have negative x plus 2 is equal to 1/2 x plus 14. So let's name this case 1, case 2. Let's call this one 3. So in this one, when we have when the absolute value of x plus 2 is positive, we'll have x plus 2, and that's equal to negative 1/2 x plus 2. And in this case, when it's negative, we'll have negative x plus 2 is equal to 1/2 negative 1/2 x plus 2. And this one is case 4. So we can solve this very simply. We would just go through each and every single one of these cases and solve. It can be tedious, and sometimes you'll face absolute value problems where you have a lot of inequalities and you just have to go case by case by case. It's tedious, but it's not too difficult. As long as you keep your work organized and your workflow normal, you should be good. So let's start back with case 1. Let's solve for x. So we have x plus 2 is equal to 1/2 x plus 14. Let's isolate for x. So this becomes x 1/2 when we bring this to this side, and that becomes 14 minus 2 is 12. We get x is equal to 24. Good. On the other side, let's multiply both sides by negative 1. We get x plus 2 is equal to minus 1/2 x minus 14. And we bring x to this side, we'll get 3 over 2 x is equal to, bring that onto that side, we have negative 16. Okay, and then now to solve for x is equal to negative 16 multiplied by 2 over 3, and this is equal to negative 32 over 3. Perfect. Moving on, we'd have x plus 2 is equal to negative 1/2 x plus 2. Bringing the negative 1/2 x to one side, we'd get 3/2 x. Bringing the 2 to the other side, we're going to get, this should be, that's a 2, yes. I thought that was a 12 for a second. That's a 2. That should be 0. X is equal to 0 then. That works out pretty well. Last but not least, we'd have x plus 2 is equal to, I'm just going to skip that step and multiply everything by negative 1 minus 2 as such. This is an x. And then bring the x onto the left side, all the x's to the left side, all the constants to the right side. We're going to be left with 1/2 x, and that's equal to minus 4. X is equal to minus 8. Great. So let's order our solutions. X is equal to negative 32 over 3, negative 8, 0, and 24. And that's our solution. Again, you can plug these in and check to see if they hold true. All of them hold true. I went ahead and checked that for you. So yes, this is solved. Perfect. But now let's talk about absolute values with inequalities. We're going to move on to this section. So absolute inequalities. So you guessed it, an absolute value with inequalities is just some absolute value expression with an inequality Boolean operator. Let's just put 0 here. So what are some rules involving how we deal with these absolute value inequalities? So let's erase this. Let's put rules. So for the first, we have x minus a is equal to d. This we've encountered. This is just the expression, so no inequality symbol. That is that x minus a is equal to, x is equal to a minus d, or we have x is equal to a plus d. For the second example, or the second rule, we have x minus a being less than d. In this case, we have a minus d being x being greater than a minus d, and a plus d being greater than x. For the next one, and I'll touch on these shortly, we have x minus a less than or equal to d. This is just an extension from the previous one, a minus d less than or equal to x, or greater than equal to, less than or equal to x, and x being less than or equal to a plus d. And these important. You really need to know these ones. Last but not least, we have x minus a being greater than d. And in this case, we'll have either x is less than a minus d, or x greater than a plus d. So yeah, as mentioned, these two are the most important. We might touch on this one, but for the most part, rules 2 and 3 are very important. It essentially tells you that you can write the absolute value with an inequality using two separate inequalities. We can use an intersecting, a combined inequality. And in the example problems, you'll see the necessity for that. So without further ado, let's hop into example problems. So for the next example 4, the absolute value of 3x minus 7 has to be less than 2. So solution, how do we do this? Recall, we just wrote down rule 2, and it states that we can treat this absolute value as the middle point, or a value in between a plus d and a minus d. So in this case, let's do that. So we can go 3x minus 7, removing the absolute value sign. And we have this is 2, and this is negative 2. Adding 7 to both sides, we would have 5 on this side, 3x, and then over here, this would be 9. And isolating for x, we would get 5 over 3, and this becomes 3. And this is our solution in interval notation. We'd have 5 over 3 to 3. And that's our answer. And we just use this. We just use this rule to get rid of the absolute value sign and treat it as the in-between point of two values relating to the absolute value. Great. Let's do another example, a little bit similar to this. In this case, the absolute value of x over 2 minus 1, and that's going to be less than or equal to 1. So now, following rule 3, which is very similar to rule 2, it's just got the less than or equal to sign, we would have x over 2 minus 1 being less than or equal to 1 here, and greater than or equal to negative 1. Adding 1 to both sides, you get 0. X over 2, 2. Multiplying everything by 2, you'll get 0 and 4. as your bounds. So our solution in interval notation, 0 and 4. And that's including 0 and 4, the square brackets, because we have the equal to under the Boolean expression. Great, not so bad. So the last example will be a bit more involved. So let's write this down. X plus 1 and the absolute value of x minus 3. So there's multiple ways to solve this, but I think the most intuitive way would be to bring everything to one side, use some checkpoints, and then check the intervals. And I'll show you what I mean by that. So let's bring everything to the left-hand side, x minus 3 greater than 0. Now we have this expression. We need to check when the absolute value signs change. So in this case, we have the absolute value of this one changes when x is equal to -1. It goes from negative to positive after -1. And in this case, it will go from positive to negative at 3. So we have these points where we need to check. Let's use the number line. We need to check these intervals. So we have -1 here and 3. So we need to check the value when x is less than 1 or -1, in between -1 and 3, being case 2, and case 3 is as such. And I'm going to make this an expression that is equal to 0. So x plus 1 minus x minus 3 is equal to 0. And I'll show you why. So for case 1, when we do this, if we're operating within this range, -1, this means that this absolute value is negative and this absolute value is negative. Meaning we're going to have negative x plus 1. This becomes a positive because a negative by a negative is positive. X minus 3 is equal to 0. Then we just get our x's canceling each other out. And we'll get -4 is equal to 0. And -4 is equal to 0. This is false, which means it's inconsistent. Can't use this case. Let's use case 2. In case 2, we're working within this range. We have x is between 1 to 3. So when x is between 1 to 3, the absolute value of this guy becomes positive, and this one stays negative. So knowing that, this expression is positive, x plus 1. This one stays negative, so we keep our positive symbol. X minus 3 is equal to 0. Now adding like terms, we get 2x is equal to 2. So we added these guys and brought the constants to the right-hand side. And we obtain that x is equal to 1. Perfect. So checking the last case now. Ooh, did I make a mistake, I think? Yeah, that's not true. 2x. I guess I'll go slower. Becomes minus 2 is equal to 0. 2x is equal to 2. X is equal to 1. Yeah, just noticed that last second. So now that we have x is equal to 1, let's check the last case, case 3, where we're in the positive region. We're here. We know that both of these, x plus 1 and x minus 3, are positive. So we can say that we have x plus 1, and this becomes negative x minus 3 because that's what it originally was. We have our like terms canceling, so we have x and x canceling, so that gives us a 0. And now we have 1 minus -3, that becomes a positive, so this becomes 4 is equal to 0, 4 is equal to 0, which is false. And that doesn't tell us anything about x. So we can write down x beside this one. Let's put a check mark here. Great. I'll write this divide right here. So now that we know that x is equal to 1 is the only, I guess, case in which it proved correct. So when we had, in our case 2, between x is equal to -1 and 3, we're now going to work with the inequality, and I'll put another number line. And I'm going to put 1 on this number line. I'm going to put 0 here, and I'm going to put 2 here. So in this case, we need to check the points greater than or equal to 1 or less than 1. So we need to check this side, or sorry, greater than 1 or less than 1. We need to check that side. Great. So case 1, I'm going to call it case 1 prime, not to confuse it with the other one. Case 1 prime, and we'll call this case 2 prime. Bad spelling. Case 2 prime. When x is less than 1. So when x is less than 1, let's check what this inequality looks like. We'll use the test point, x is equal to 0. Great. So we write our inequality down, x plus 1 minus x minus 3 greater than 0. So using 0, we'll get 0 plus 1 minus 0 minus 3 greater than 0. So we get 1 minus 3 greater than 0. That's -2 greater than 0. And this is false. So case 1 prime does not work. Case 2 prime. When x is greater than 1, let's use test x is equal to 2. We'll go with the absolute value of 2 plus 1 minus the absolute value of 2 minus 3. And that has to be bigger than 0. Well, it turns out that this is 3, and this becomes 1, and that needs to be greater than 0. We know that 2 is greater than 0, so this case is true. So that this is here. So in interval notation, our only region in which it worked was when x is greater than 1. So we say we go from 1 to infinity, and we'll square that for that solution. So to recap that problem, all we did is first we analyzed the inequality itself, and we checked the points in which the inequality signs change. So there was 3 cases where the inequality sign would change. So between case 1 was anything less than -1, case 2 was anything between -1 to 3, and case 3 was anything above 3. We found out that case 1 right here had no solutions. We found that case 3 had no solutions. But in between case 2, we did have a solution. We had x is equal to 1 was positive. It worked as a true solution. So then, analyzing the inequality itself, we took x is equal to 1 and checked each side of the inequality. Then checking each side of the inequality, we found that case 1 case 1 prime, where x was less than 1, we found that to be false. But when x is greater than 1, we found that to be true. So we have our interval between 1 to infinity. And yeah, overall, we talked about the actual absolute value, what this represents, the definition of absolute values. Then we talked about some of the properties of absolute values, absolute value equations. Then we talked about some of the rules between absolute values and working with inequalities, and some example problems to wrap it up. So feel free to leave a like, subscribe, share it to anyone you feel like it's necessary. And in the next video, we'll continue with our pre-calculus notes before we begin any calculus. Thank you.